And indeed, I would like to discuss some questions concerning concentration of measure for convex functions. This is based on joint work with Michał Strzelecki, who is a PhD student at the University of Warsaw. And in order to motivate the concentration of measure theory for convex functions and also to put it in the right context, I will need to briefly describe the classical theory of concentration of measure for all Lipschitz functions. And I will need to introduce some definitions which, well, perhaps they are, there are some people here for whom those definitions are new. So for future reference, I put them here in the abbreviated form, but they will also appear on the slides, of course. So for the moment, you can ignore this blackboard. OK, so let's start with the first definition, which in fact is somehow self-explanatory, because, well, we will say that a probability measure on some metric space satisfies a dimension-free concentration inequality. I will denote it by Ci to infinity. I will explain in a moment why. So this inequality holds if we have some non-trivial rate function. By non-trivial, I mean that it vanishes at infinity, such that for all positive integers n, when we look at one Lipschitz function on the n-fold Cartesian product, and we look at how it is concentrated around its median, and the median is calculated here with respect to the product measure, then we will have a tail decay governed exactly by this function alpha. So this is, I guess, the only thing that you can call the dimension-free concentration inequality. So I will often use this, let's say, semi-probabilistic notation. So I will treat functions as random variables, and I will write, for example, the median or the expectation, and in the subscript, I will write down the measure according to which it is taken. So just to avoid ambiguity, let's think, it doesn't matter really, but let's think of it as being the smallest median. Right? So why Ci to infinity? Of course, Ci for concentration inequality. Infinity, because what is crucial here, alpha is chosen independently on n, so we can go with n to infinity. And 2, because, well, I should have said it, I only wrote it down. To make it meaningful, we should say with respect to what metric on the product space we regard those one Lipschitz property. And on the product space, we will always consider this L2 type metric. So that's why 2 here. So there are many examples by now in probability. The most classical ones are the uniform measure on the sphere and the Gaussian measure. Also, there is the exponential measure, and the first two, in fact, satisfy this concentration property at a sub-Gaussian rate. So this function alpha of t can be taken as e to minus ct square for some constant c. And it turns out that this is the best we can hope for in non-trivial cases, because simply by the central limit theorem, right? We know that if we look at sums of independent random variables, the tail should be somehow exhibit some Gaussian behavior. So we cannot hope for anything better than the Gaussian tail. At the same time, it turns out that whatever concentration property with non-trivial alpha you have, if it's dimension-free, it can be boosted to sub-exponential concentration property. So we can always find C independent of n, such that this holds with alpha of this form. This was observed by Michel Talagrand. OK, so this concentration properties, if it's dimension-free, it's somewhere between exponential and sub-Gaussian. So how do we prove such inequalities usually? So I would say that there are 3 main ways to prove them. So there are functional inequalities, for example, Poincaré or modified Locke-Sobolev, transportation cost inequalities, and their duals, which are infimum convolution inequalities. So in all those cases, the idea is that we want to propose a type of inequality for which it is easy to pass from the measure to the tensor product. Once we know that the inequality holds for mu, it is very easy to show that it holds for all tensor products and the constants do not change. So of course then It's a challenge to prove that this inequality holds for mu, but this tensorization allows to obtain dimension-free concentration. So let me describe first the Poincaré inequality, which is probably the most important one here. So for now, we'll be still, well, everyone knows what the Poincaré inequality is, but let me explain it anyway, because we are here on a metric space. Like in the Poincaré inequality, we have lambda times the variance of f should be smaller than the second moment of the gradient, right? But what is the gradient here? So in fact, we do not define the gradient. We just define something that is called the length of the gradient. And we define it by this formula. So it should hold for all local Lipschitz functions, which makes it nicely defined. And of course, if you are on Rn or on a Riemannian manifold and f happens to be really differentiable at x, then this will coincide with, we have the true gradient then, and this definition will coincide with the Euclidean length of this gradient, so we recover the usual notion. But this is useful not only for metric spaces, but also on Rn if we deal with measures, for example, which are not absolutely continuous, right? So to have it defined pointwise. And what's the connection with concentration? So it was first proved by Gromov and Millman in the 80s. So whenever mu satisfies the Poincaré inequality, then it satisfies this concentration, dimension-free concentration inequality. And it was before Talagrand observed that you can always obtain this rate, so they proved directly that Poincaré inequality gave this rate here. And since it is known that the standard exponential distribution satisfies Poincaré inequality, it is in some sense optimal. So in this talk, in general, I will not be concerned with the precise values of the constants, right? So if the rate is correct up to some constant in the exponent, I will still call it optimal, contrary to, for example, the talk by Professor Banuelos. All right? So it turns out, it is a much more recent result, that this implication can be reversed. If we have this dimension-free concentration inequality, then in fact, we have the Poincaré inequality in the form we saw before with this length of gradient. So in fact, it turns out that we have such equivalences. Any dimension-free concentration inequality is equivalent to concentration inequality at a sub-exponential rate and equivalent to the Poincaré inequality. So one could say that this gives some rather general description of measures satisfying the concentration inequality. But it turns out, and okay, we know that this is the best we can hope for general one-Lipschitz functions, but it turns out that in some situations which are of interest, one can in fact obtain a stronger inequality, a stronger concentration inequality, if one takes into account some additional information about the function. And before I describe the inequality, I will show the tool for it. This is a combination of two results by Bobkov and Ledoux and Bobkov-Gentil-Ledoux. So it turns out that if mu satisfies the Poincaré inequality, then the first result is that it satisfies some sort of logarithmic Sobolev inequality. So what do we have here? Here is the entropy of the function e to f. Let me recall the definition of the entropy. And it is bounded by such an expression. You can think of it as some energy functional. But it holds only for functions for which the gradient, the length of the gradient, is bounded pointwise by some constant c. So I don't have much time to comment on it, but let me perhaps just say that if we had this inequality for all local Lipschitz functions without this restriction on the gradient, then this would be the usual Locke-Sobolev inequality introduced first by Gross. It would be equivalent, just written in a different form, but equivalent to the one that Professor Banuelos mentioned in his talk. And such an inequality, without this restriction, would imply sub-Gaussian concentration. So here we know that Poincaré can imply only sub-exponential concentration because we know those examples, like the exponential measure for which Poincaré holds and the concentration is not sub-Gaussian. So the idea by Bobkov and Ledoux was that, well, the full Locke-Sobolev inequality cannot hold for the just under the Poincaré inequality. So they wanted to restrict it, weaken it somehow, so that it would be related to Poincaré. And this is the restriction. We do not look at all functions, just at functions with small gradient. And then in the second paper, they proved that such Locke-Sobolev inequalities, they are usually called modified Locke-Sobolev inequalities, imply something that is known as transportation cost inequalities. So perhaps let us start here, disregard those definitions for the moment. Let me first introduce the transportation cost. Imagine that we have two measures, and in general, the transportation problem is about finding some transportation plan which maps the measure mu into the measure nu. So we can, usually it is pictured with like two piles of sand, and we want to move one of them into the other one. Of course, we can try to do it with a single function in which everything, all the sand above one point, is sent to the same place. But if we want to relax it, we can say that we can redistribute sand above a fixed point everywhere on the space. We have no restrictions. So then this can be described mathematically as looking at the couplings of measures. So we have two measures, mu and nu. We want to move mu into nu, and we look for a coupling, a measure with marginals mu and nu, and then this, in this coupling, the conditional distribution of the second coordinate with respect to the first one will tell us how the sand lying above one point will be distributed all over the place. So if we imagine that for transporting a unit mass from x to y, we pay some cost theta of x minus 1, then this integral will be the total cost of our transportation plan, and the infimum will give us the optimal transportation. Right? So, of course, everything depends on the choice of this theta. If theta is just the Euclidean norm, this would give us the Wasserstein Kantorowicz distance that appeared yesterday in one of the talks. If theta is x squared, then this would be the distance going back to Monge. And it is known, again by Talleyrand, he did a lot in this area of concentration, that, for example, for the Gaussian measure, if mu is the Gaussian measure and theta is this square of the Euclidean norm, then whatever measure mu we take, this transportation distance, it's not a distance really written like that, but let's call it distance anyway. So somehow the measure of proximity, maybe it's a better name, between the Gaussian measure and any other measure is bounded by the relative entropy of this new measure with respect to the Gaussian measure. So here we have two notions of proximity between probability measures, and it turns out that one of them controls the other one. So again, such an inequality for theta being the square of the Euclidean norm would imply Gaussian concentration. We cannot hope for it under the Poincaré inequality. So the idea of Bobkov, Gentile, and Ledoux was to weaken this cost function, and this is what is done here. So please do not pay attention to the constants. This is just chosen in such a way to make it a nice, smooth, convex function. We should think of it like that. For x relatively small, relatively close to the origin, this behaves like the square of the Euclidean norm, and then it grows not quadratically but linearly with the distance to the origin. So of course this is smaller than just the square of the Euclidean norm, and that's why the Poincaré inequality can imply such transportation cost inequality. So again, whenever something is close to our measure satisfying Poincaré in the relative entropy sense, it is close in this transportation sense. So why is it interesting from the point of view of concentration? So I already mentioned it. It turns out that we can get improved concentration. In fact, it follows from both of those results. And so let me write it only in the Euclidean space. So we have Rn, this is our reference space, and then we take the Cartesian product. And when we have a function, well, we can think of the Lipschitz constant as the supremum of the Euclidean length of the gradient. But it turns out that if we look also on the tensor product at the partial gradients along each of the copies of R little n, and take the maximum of their norms, then we can get something that is called a two-level concentration inequality. This L1 is smaller than L2, always, so we can interpret it as follows. So for small values of t, the tail of the function will behave in a sub-Gaussian way, and only later it will appear in this sub-exponential way. Of course, it has to be sub-exponential for large t. So perhaps it's best to look at it for n, little n equal to 1. Then this L1 is just the L infinity norm of the gradient, right? The maximum size of the partial derivative. And let's look at a simple example, just at this sum of coordinates normalized by square root of n. So from the, let's say, analytic point of view, this normalization gives us the Lipschitz constant equal to 1. Right? So the Poincaré inequality would give us such tail behavior. But from the, okay, before that, in the Poincaré inequality, I wrote median. It doesn't matter. If you have any concentration of this type, median and expectation are so close one to another that by modifying this constant c, you can pass from one of them to another one. So this is what Poincaré would give. But we know from the probabilistic point of view that this is not satisfactory because from the central limit theorem, we would like to see some Gaussian behavior, right? And the modified Locke-Sobolev inequality would exactly give t squared for small t, and then square root of n, capital N times t. And you can see that in larger and larger windows, we get this Gaussian behavior. So this example of this function is rather trivial because it can be obtained, for example, from some versions of Bernstein's inequality for sums of independent random variables. But such a phenomenon where you can get better concentration by looking at the other norms of the gradient are also present for other functions. This is just an easy one. Okay, so let me summarize. So we had all those different definitions starting from this dimension-free concentration equality. It turned out to be equivalent to sub-exponential concentration equality, and then we could see different descriptions. This is all equivalent because the last inequality we have here implies dimension-free concentration. So in fact, we can close the cycle of implications, right? So we have Poincaré, then modified Locke-Sobolev inequalities, quadratic linear transportation cost inequalities, and two-level concentration. So it turns out that such equivalences are characteristic in some sense for this exponential concentration. If we insist on stronger concentration, there will be just implications here, certain implications, but not equivalences. Okay, so now I can finally pass to the real topic of my talk. So I would like to discuss concentration in the situation when we are not interested in all one Lipschitz or Lipschitz functions, but just in convex functions. So it makes some sense from the point of view of applications because, well, especially in like asymptotic convex analysis, in functional analysis, or even in statistics, quite often we deal with functions which are convex, like, for example, in geometry or in functional analysis, we want to apply concentration of measure to norms. So one can rewrite the previous definition. It is exactly the same as before. We want the tails of functions with respect to the tensor product measure to decay at a rate independent of the dimension capital N. This x should be r little n now, of course, right? But now we want it not for all one Lipschitz functions, but just for the convex ones. And now you could ask if such a relaxation of what we want to get will allow us to somehow relax also the assumptions of the measure. How far the usual concentration for all Lipschitz functions is from this one. It turns out that it is in some sense far because the previous dimension-free concentration for all functions, as we know already, is equivalent to Poincaré inequality. So when you think about the Poincaré inequality, you will see immediately that it imposes restrictions on the measure, for example, on the support. If, for example, the support is not connected, then you can create a function like this with the derivative vanishing on the support, but which is not constant on the support, right? So the variance is not 0, but the second moment of the gradient is 0, the Poincaré inequality cannot hold. So one necessary condition for the Poincaré inequality is the connectedness of the support. On the other hand, again, we have Talleyrand here, a theorem by him which started this whole story says that all measures with bounded support on Rn satisfy this convex concentration inequality. So for example, we have it on a discrete cube with dimension-independent constant, which gives some improvements over the Kinchin inequalities. So as we can see here, somehow the problem seems to be rather different from this less local in some sense than in this class of all one-Lipschitz functions. So we can ask, having this picture of equivalent formulations in the classical case, if something like that holds also in this convex world. And first we should ask what the counterpart of different notions should be. So it is easy, like for the convex concentration, I just added the word convex, right? It is the same for the Poincaré inequality. Here I wanted the inequality to hold for all locally Lipschitz functions, well, convex functions are locally Lipschitz, so here I just want this inequality to hold for all convex functions, right? And later on I will explain how to somehow translate, find counterparts of the other notions here. So let me also mention that here we have a slightly annoying complication. We have to deal with upper and lower case separately. Let me go back here. You see, if we want this inequality to hold for all one Lipschitz functions, I could remove the absolute value here, and then I could apply the inequality to f, to negative f, use the union bound and get this inequality with additional constant 2 here, which in this theory is okay, right? We just want even here the existence. Now, if I impose this assumption for one Lipschitz convex functions and remove the absolute value, I cannot pass to negative f because it will not be convex anymore, right? And that's why there are some technical complications here in formulations of certain things. Nevertheless, at this basic level, so first on the real line, it was proven by Bobkov and Goetze, and then on Rn by Gozlan, Roberto, and Samson, it turns out that a measure satisfies this convex concentration inequality if and only if it satisfies Poincaré inequality for all convex functions. So this is exactly like in this classical setting. Now, Gozlan, Roberto, and Samson also proved that if we have dimension-free convex concentration from above, so this is a priori not the same as before, right? At any non-trivial rate, then it implies the sub-exponential rate also from above. And this also implies already the Poincaré inequality. So it's enough to have the upper tail with a dimension-free inequality to get Poincaré. So again, it resembles what we saw before, but here not completely. Right? And now, okay, I should explain that similarly, like the second notion that I mentioned after the Poincaré inequality was this notion of modified Locke-Sobolev inequalities. So we have the estimate of entropy of functions which have small gradients in terms of some energy. So with Poincaré, it was enough to add the word convex, right? Because the variance does not change if we multiply the function by -1. But here in modified Locke-Sobolev inequality, it makes a difference if we look at the entropy of e to a convex function or e to a concave function. So again, we have two notions now. We have the modified Locke-Sobolev inequality, which is exactly the same for convex functions, and an inequality of the same form for concave functions, right? So we have two types of inequalities. And a similar thing will be seen in this setting of transportation cost inequalities, but here things are even more complicated because, well, here at least this modified Locke-Sobolev inequality is expressed in terms of functions, right? But for the transportation cost inequality, it is not the case, right? This is expressed only in terms of measures. We will say that for every measure mu, this transportation cost should be bounded by the relative entropy. There are no functions here. So the question is what we should replace this notion of transportation cost width to get something suitable for investigation of this convex dimension-free concentration. And the answer to this question appeared implicitly already in the papers by Katalin Martin in the 90s, but it was further investigated to great extent, again, by Goslan, Roberto, Samson, and Tetali. So now the notion of the transportation cost between mu and nu is a little bit different. We again look at the infimum over all couplings of our measures mu and nu, but now we decompose such a coupling using this conditional expectation of the second, conditional distribution, sorry, of the second coordinate with respect to the first one, and we move one of the integrals inside, right? So in terms of random variables, it's perhaps more readable. We look at an infimum over all pairs of x and y, where x is distributed according to mu and y according to nu on the same probability space of such an expression. So now it is clear that if we use Jensen's for the conditional expectation and we go with this expectation outside, we will recover the previous notion, right, of the transportation cost. So this one is smaller, and one can hope that, right, so inequalities with this on the left-hand side will be weaker, and perhaps they will correspond to this convex world. So it turns out that this is indeed the case, but I should first define those inequalities, because now, again, we have two choices. Our transportation cost is not symmetric anymore. Right? So before that, our transportation cost inequality was just that transportation cost is bounded by the relative entropy. So let's say that we want to keep the relative entropy on the right-hand side, but then we may ask what transportation cost we should put on the left-hand side because it is not symmetric. So we have two options. It's bar t plus and bar t minus. And depending on the order in which we put those measures on the left-hand side. So it turns out that, not surprisingly, right, that one of those inequalities will correspond for the upper tail of convex functions and the other one for the lower tail. So t plus is responsible for the lower tail of Lipschitz convex functions and t minus for the upper tail. And we will say that t bar is satisfied if both of those inequalities hold. Right? So as you can see, somehow, at many steps, we have two inequalities in place of one. So having all those definitions, have a result which is a consequence of many works, but it turns out that first that on the real line we get the same picture as in the classical case. It's just that now we add the word convex at the right places and we replace this usual transportation cost inequality with this weak transportation cost inequality. And again, the cost function is this quadratic linear. First, it is quadratic, and then it grows linearly. So this is on the real line, and in fact, I put here all the relevant papers, but you don't need all of them to close the cycle of implications. In fact, you need the paper by Bobkov-Getze and all the papers by Natalia Goslan and co-authors. Because in some other papers, some other implications, like jumping above this line of implications, were proved. And this is on the real line, and the thing is that it is indeed a real line argument. Namely, Bobkov and Getze, back in the 1990s, proved a very simple characterization of the convex Poincaré inequality in terms of the tail regularity of the measure on the real line. And many of, not all, but many of the proofs here go like that. Well, for example, if the convex Poincaré inequality is satisfied, then this condition, one-dimensional condition by Bobkov-Getze holds, and then working with this condition, one can prove, for example, the modified Locke-Sobolev inequality. So one cannot hope to obtain such a characterization. I believe it's a difficult problem, really, for arbitrary dimension. So it's not clear how to generalize the approach from this paper to the general setting. At the same time, this thing was quite general in the classical world. So one can ask if perhaps mimicking some of the proofs from the classical world and modifying them, that perhaps you can obtain this picture in Rn. So this is indeed our result. So it turns out that we have the same equivalences in general case for measures on Rn. Dimension-free concentration for convex Lipschitz functions is equivalent to all the other inequalities I mentioned before. And okay, to be more specific, some of those implications, I even showed them before on some slides. So some of them were known. And what we did was passing from Poincaré to modified Locke-Sobolev and then to this transportation cost inequalities. So this is the theorem formally. So if we have a probability measure satisfying such inequality for all convex functions, then it satisfies this modified Locke-Sobolev inequality for f convex and f concave, provided that the gradients are bounded uniformly. And also we have this inequality T plus, which amounts to two estimates. Those transportation costs in both orders, between mu and nu, between any measure nu and our measure of reference, are bounded by the relative entropy, with the same cost as before, first quadratic, then linear. So this is exactly the same. However, well, maybe going here, or perhaps even to the previous slide, and seeing those equivalences, one could think that this is perhaps the ultimate result, but this is not the case, because there is something hidden in the formulation I showed you before, but which is not quite satisfactory. So it turns out that when we deal with concave functions, so with this inequality T plus, with this modified Locke-Sobolev inequality for concave functions, if you want to prove it, starting with the Poincaré inequality, we obtain constants which depend not only on lambda, but also on this dimension little n. So it still gives dimension-free concentration, because remember, the dimension-free concentration was about something like that, and our constants, fortunately, do not depend on this capital N. But in this field, like, having constants depending on this little n is really not very satisfactory. So the problem is just with this lower tail of convex functions. This is not the case, for example, for this inequality Barty minus. There we have constants depending only on lambda. And when one looks at our proof and works a little bit harder, one can reduce the problem of eliminating this dependence on the dimension to the following question. So we were asked to pose open problems. So the question is formulated quite easily. Assume that we have a probability measure on Rn, which satisfies this convex Poincaré with some constant lambda. So then we would like to have this dimension-free concentration, or deviation, below the mean, at the exponential rate, but with constant depending only on lambda and not on the dimension little n. And it is a strange question in some sense, because when you ask people working in this area whether something like that holds, and also our first impression was that this should be obviously true. I mean, there are so many ways of deriving concentration from the Poincaré inequality that one of them should work. And then it turns out that whatever classical approach you take, at some point it breaks down for silly reasons. Like, for example, at some point you have to do some truncation which will lead you out of the class of convex concave functions, and then you cannot apply the next step. Or, for example, you want to look at the Laplace transform, right? But when you look at e to the f, and f is convex, this is convex. When f is concave, well, this doesn't have any special properties which you would like, in general, which you would like to apply. So it may be very well the case that this is something very easy, but we are somehow biased by the previous approaches. We asked several people, and usually the answer was something like, oh, it should be true, or, for example, it should follow from this and this paper, and then we would get an email on the next day, oh, sorry, there is a problem with this approach. So I really don't know. Perhaps it's like a half-a-page argument, or perhaps it's nothing difficult, but somehow we got stuck on this, and I don't know. Okay, so if I have one more minute, let me just say a few words about the proof. So, to be honest, the proof is not very difficult. So given all the contributions that were before us, it was based on a modification of previous approaches in which you had to work a little bit to make them work in this convex setting, but it's possible. In fact, this we were happy about. It turns out that we already also got some simplifications of the original arguments because of this necessity to work with the convex setting. Of course, anything that is, maybe not of course, but if something can be proved here, usually the corresponding argument will also work classically. So we use the approach by Bobkov-Ledoux for the modified Locke-Sobolev inequalities. And then to pass from them to the transportation cost inequalities, we use the dual form of them. So maybe let me just comment on this dual form. It was first introduced in a slightly different form by Moret in the beginning of the 90s. So it turns out that this inequality, here I will write it just for T minus, for one of those two inequalities from the convex setting, is equivalent to such an inequality. So here we have Q1 of f, which is the inf convolution of f with our cost. And in general, here we have this QTF, which is a nonlinear semigroup related to the Hamilton-Jacobi equation. And it turns out that if you write down this inequality, like look only at the first factor here, take the logarithm, and calculate the derivative, and well, this QT, I mean, you don't look at Q1, but at Qt. This Qt will appear there, and combining this Hamilton-Jacobi equation with those modified Locke-Sobolev inequalities will allow you to prove that this function is non-increasing. And then looking at the behavior around 0, you will get this inequality. So it is based strongly on this approach by Bobkov, Gentil, and Ledoux. But for this, we need this characterization, dual characterization, which was, again, obtained a few years ago. OK, so that's all. Let me stop here. Thank you very much.
Questions or comments?
So I understand that one advantage is that there are much more measures.
Yes, exactly. Like this is best seen, I guess, in this bounded support setting, because then you don't have any assumption on the measure, just the bounded support. And of course, the inequality is expressed in terms of the size of the support, right, of the diameter. But also here, like, for example, those inequalities are characterized on the real line. And somehow, again, you see that it doesn't matter what happens on compact intervals. You still need some regularity of the tail, but just asymptotically, right? For large, something should hold for large enough t, for example, some regularity condition.
This regularity is fast decay?
It's not enough to have just fast decay. It's more like it should be a regular decay. So, for example, for this, it should be like there should be a constant that. For large t, for the same for on the right tail and the left tail. For example, that if you shift the tail by h, it will drop by a factor of 2, right? But it's not enough to have, for example, sub-Gaussian tails, for example, is not enough to get sub-Gaussian concentration inequality, right? Or sub-exponential tails is not enough to get sub-exponential inequality for convex functions. You need some regularity in how the tail decays, really. Thank you.